All right, my friends, are you ready? Are you ready to build that dendrogram and use it to find the optimal number of clusters? Here we go, let's implement the solution together. So let's start by creating a new code cell. And now, what will be the first step? Well, as usual, we want to implement this efficiently. So we're gonna use a function, but this time, exceptionally, this function won't be imported from scikit-learn. It will actually be imported from another very popular library in data science. I would say, it is in the top 3 most popular libraries. I put scikit-learn first, of course, and TensorFlow for deep learning, but that other library is SciPy. SciPy contains a lot of great tools when building machine learning models, and well, for hierarchical clustering, it indeed contains a function which is called dendrogram, and which will return the dendrogram itself, the plot of the dendrogram. So let's do this. Let's directly import that, module first that contains this function. And as we said, this model is taken first from SciPy, then from the module cluster, and then from the submodule hierarchy. Right? Google Colab guesses it perfectly. The other way to write this is, of course, to say from SciPy import cluster.hierarchy. So that's just another writing. And then we're going to add, of course, a shortcut to this. Otherwise, we would need to call all of this again. And the shortcut will be as SCH, right? For SciPy cluster hierarchy. Okay, so that's the module which contains the function we want to use in order to build our dendrogram. So now, next step, well, the next step is to use that function which we can now access from that hierarchy module which we just imported. And since this function returns directly the dendrogram itself, well, we're going to create a new variable here which we're going to call dendrogram. As simple as that. And this dendrogram variable will be the output of this dendrogram function which we're about to use from the hierarchy submodule by the cluster module from the SciPy library. All right, so let's do this. Since this function belongs to all of this here, the hierarchy module, well, we have to call first the shortcut leading to that module, SCH, and from which now we can call this dendrogram function. Perfect. Thank you so much, Google Colab. And now, indeed, in the parentheses, we have to input some arguments, and now you can't really guess what the argument will be, so I'm just going to write it and then I will explain what this means. So first, we actually have to call SCH again, the hierarchy module from the cluster module from the SciPy library. So SCH, from which this time we're going to call another function, which is the linkage function. And this linkage function will take as input 2 arguments. First, well, your matrix of features inside which you want to identify the clusters, and that's of course X. And then the second argument is the clustering technique. And in hierarchical clustering, the most recommended method and the one that brings the most relevant results and the most relevant clusters is the method of minimum variance, which is a technique that will result in having clusters inside which, the observation points don't vary too much, have among all of them a low variance. And that's what it means, The method of minimum variance consists of minimizing the variance in each of the clusters resulting from hierarchical clustering. And so this is really the method that I recommend. And speaking of this method, that's exactly the next argument of this linkage function we have to input here. And the name of that parameter is method. And the name of that minimum variance method is not called minimum variance, but ward. Ward, you can actually check this on Wikipedia. There is a whole page on ward, and you will see that indeed it consists of minimizing the variance inside your clusters. All right, and that's it for the whole dendrogram function here. It only expects 1 argument, which is basically the method you choose for your clustering that you link to your matrix of features X in which you want to identify the clusters. So that's all you need to input here in this dendrogram. And there you go. This will already return the dendrogram itself, the plot of the dendrogram. But as usual, we want to make it nice. So we're just going to add a title, an X label and a Y label, and then we will show it. And I will teach you how to read the dendrogram to indeed find that optimal number of clusters. Are you ready? Let's do this. Let's do this quickly. We're going to first add a title, with the title function by matplotlib.pyplot. And this time, let's say, we're just going to choose a simple title like dendrogram. All right. Then let's add an X label. There you go, X label, and then in quotes. Well, you tell me, what is going to be on the X-axis? Let's not fall into the trap of, answering too quickly. The X-axis is neither the annual income or the spending score. It's none of the features. The X-axis in the dendrogram is actually the customers, the observation points. Basically, the X-axis are not the columns as I just suggested, but the rows. Because remember, in this matrix X or even this data set, each row corresponds to a customer. And this customer is actually an observation point. And that's what is on the X-axis of the dendrogram. You have all the observation points, just given by indexes from 1 to 200, because we have 200 customers in this data set. And then on the Y-axis, what will you have? Well, you will have the Euclidean distances between each pair of customers and then each pair of groups of customers, where the groups get bigger and bigger. And then by considering bigger and bigger groups, you get also the Euclidean distances between two of these bigger groups, right? So that's how the dendrogram works. It will become more clear once we visualize this. So there you go. I just wanted to get you to think on what is the X label and the Y label. So now that we know, well, let's input here the X label, which will be, therefore, you can either call it observation points if you want to generalize this, or if you want to stay in the context of this case study, well, we can call it customers. All right, customers. That's for the X label. And now for the Y label, well, that will be always the same, independently of whether we want to stay in that case study or not. That's going to be always the Euclidean distances. All right, that's always what is on the Y-axis in a dendrogram. And finally, we end up, remember, with plt.show to indeed display the graph in the output. All right, so now let's check it out. Let's see that dendrogram, and I will explain again what we have on the X-axis and the Y-axis. All right, let's do this. Let's play the cell, and we're about to get the dendrogram in a second. There we go. All right, so that's our beautiful dendrogram, and as we said, in the X-axis we have the customers listed from 1 to 200, because there are 200 customers in the dataset. And on the Y-axis, well, we have indeed the, as you can see, Euclidean distances first between each pair of customers. That's the little pairs you see here. And then as you see, when you link two customers, within a same group, well, this forms a group. And then with the group next to it, linking two other customers, well, you link these two groups within a new pair. And you compute the Euclidean distance between these two groups by, taking the root of the sum of the squared distances between the customers inside these groups. All right, and you do this for then each pair of bigger groups, as we see. For example, the two biggest groups that we see on this dendrogram are first this one, that's a first group containing lots of customers, and the second group is this one, right, which was linking these two subgroups and then all these subgroups inside. And so now the question is, how do we figure out that optimal number of clusters? Well, it's super simple, and to show you this, I will actually click these three dots here to view the output in full screen, but then that's still not enough. What I would like to do is now save image as. All right, I'm going to call this image dendrogram. I'm going to save it, and now we're going to go onto my desktop, which is right here. Yes, I'm recording at night, and here is the dendrogram. So let's see if we can zoom better now. Oops, let me just, there you go. Let me enlarge this. All right, well, it's still not that great, but it's good because what I wanted to do is this horizontal line. That's exactly what I wanted to get, which I couldn't get on Colab. And the reason why I wanted to get this horizontal line is because it is what will help us figure out the optimal number of clusters. Because very simply, on a dendrogram, the optimal number of clusters can be found where you have the largest distance you can move vertically without touching one of these horizontal bar. You know, by horizontal bar, this is a first horizontal bar, then this is the second horizontal bar, the third horizontal bar, fourth horizontal bar, and then, you know, this one is the next one, horizontal bar, etc. And the optimal number of clusters can be found where you can move that horizontal line, you know, the ones that I'm creating with my mouse, and then I'm going to try to move that vertical bar inside the dendrogram, you know, starting from the top, and we'll see where I managed to move the most vertically before meeting one of these horizontal bar. So let's do this together, and you know, we will very easily find where we have the largest vertical move, let's say, and then the optimal number of clusters will actually be the number of vertical bars we have inside that vertical move. All right, so let's start from the top. We have to start from the top. And so from the top, it goes this way. We start from here. That's the first horizontal bar. And when I move down, you know, move down like that, there you go. That's when I meet the next horizontal bar, you know, this one. So actually, we made a very small vertical distance here, which means that indeed, the optimal number of clusters is definitely not 2, right? Because here we have 2 vertical bars. Then the next step is to start from this second horizontal bar. And so let's do this with our mouse, all right? We start from here, the second horizontal bar, and we're going to go down until we meet the next horizontal bar, which is right here. This one, right? That's the second horizontal bar. This was the first. And from this first to the second, well, we made that vertical distance. Okay? So that's pretty big, which means that maybe, you know, if it is the largest vertical move we can make, well, in that case, the optimal number of clusters would be 1, 2, 3. You know, the number of vertical bars we have within this vertical move. This one, and this one. So that would go for 3 clusters. All right, so maybe that's the optimal number of clusters, but then let's continue. Let's continue from here, right? So we're going to continue from here, that last horizontal bar we met. And now I'm going to expand over here. And same, we're going to go down until we meet the next horizontal bar. And there we go. That's the next horizontal bar. And here we made a small vertical distance, so definitely it is shorter than the previous vertical distance we made just before, and therefore the optimal number of clusters is definitely not 1, 2, 3, and 4. It's definitely not 4. Okay? Okay, but let's continue. Maybe there is a higher vertical move we can make in the next step, and you know exactly that this is going to be the case because we already did k-means. But there we go. That's the next move. We start from here, that last horizontal bar we met, and I'm going to expand this in order to, you know, not miss any horizontal bar. And actually, I should even take the whole width, you know, I should take exactly this. All right, so that we can make sure we don't miss any horizontal bar. So we start from here, and here we go. Let's move down. Let's move down, move down, move down, move down until we meet the next horizontal bar. And here we go. Right, you see? That's the next horizontal bar we met. The one from that last cluster here. And, well, now the question is that vertical move, you know, vertical distance we just made here bigger than the one we made in the second step, meaning this one? Well, it seems to be the case, right? It seems to be that this vertical distance is actually larger than, you know, this vertical distance. How could we actually measure this, you know, to be exactly sure? Well, have a look at, you know, the pixel here. 264 times 66. I don't know if you can see it well, but if I move up, you know, remember that was 66. Well, actually 0. Okay, so that's very easy. So there are actually 66 pixels here. All right, cool. And now let's do this again here from that horizontal bar and up to here. And wow, okay, so that was very short actually, because here the vertical distance is actually 67 pixels. You see it? You know, 272 times 67. 272 is actually the width of that rectangle I just made with my mouse, and 67 is the height. And that's the height we're interested in because that corresponds to the distance of the vertical move. So actually 67 versus 66. So, well, you know, 3 clusters is actually a good number of clusters. But you know, since we already did it with k-means and on the elbow method, we clearly identified that the optimal number of clusters was 5. Well, we're going to take that 1 pixel difference here in order to still keep, well, 5 as the optimal number of clusters. But it's really interesting that we did this dendrogram. I actually didn't notice before that we were so close. From my vision, I had the impression that this distance was larger, but there you go. This one was also very good. Let's check it again because I just want to make sure. Yes, 66, but even, 67 depends down to where you go exactly in that horizontal bar. Actually, to make it super thorough, we would need to start from here, at the bottom of the horizontal bar up to the top of the next vertical bar. So here we have 65, and here for that next distance, well, I'm starting from the bottom of the horizontal bar and going here. 65, the same. It's the same. So actually 3 clusters of 5 clusters is very good. And so feel free to, continue this implementation with either 3 or 5. But since with k-means we identified 5 clusters as the optimal number of clusters, well, we're still going to go with 5 here. But there you go. That's a very good example because indeed in some situations we can have 2 optimal number of clusters. All right, so I'm really glad I showed you this, and mostly this shows you the importance of trying several models, whether it is for regression, classification, clustering, because indeed having another model can give you extra insight when doing your machine learning task. And indeed with hierarchical clustering, that extra insight is that indeed 3 clusters actually makes a lot of sense as well. So there you go, make sure to keep hierarchical clustering in your toolkit in order to catch these extra insights in your future datasets for your future clustering problems. All right, perfect. So let's close this and let's go back to our implementation. Here it is. All right, so to close this, well, I just pressed escape and there you go. We have our dendrogram. Everything is perfect. And now for the next step, we're going to train that hierarchical clustering model with, as we said, 5 clusters, but you can totally do it with 3 clusters if you want. It will still bring amazing results. And so let's do this together in the next tutorial. And until then, enjoy clustering and machine learning.